Good morning. My name is Ömer, and today I'm honored to be presenting at the GTT Users Meeting 2023 to discuss about the high-throughput screening of composition space for materials and process design. Let's begin by mentioning that many material design or process questions often involve a multitude of input variables, and we are trying to understand the thermodynamic and physical properties of our system by defining these input materials and conditions of interest. However, the material systems gets very complicated as the amount of elements in the system increases. For example, the smartphone in our pockets consists of 40 elements. Imagine the complexity of a chemical space defined by 40 dimensions. Just for comparison, everything we can observe is in a three-dimensional space. So it's a huge space when we say a 40 dimension with 40 elements. Material informatics in this context can be used to narrow down the relevant chemical space of interest. Now, let's dig deeper into the screening approach with the help of a practical example. We focus on the design of a hard-facing alloy for mining or agricultural applications. Specifically, we will consider the laser cladding process parameters, which plays a crucial role in the material properties. And laser cladding involves the use of a laser beam, as you can see on the animation, to fuse a coating layer on a substrate, creating a hard and wear-resistant surface. For this particular test case, several computable criteria has been identified to guide us our screening process. First of all, we aim for a small melt range to avoid cracking. Additionally, we seek to achieve austenitic solidification, martensite transformation, and also to prevent embrittling phases. Density on and the cost of the raw material, we will also cover these aspects, and they are also important considerations. Moving on to the composition space, it consists of 12 elements, each with different limits and step size criteria. This elemental combination range gives us around 767,000 compositions to analyze using backstage equilibrium calculations. Given the size of the data, I utilized the ChemApp for Python, which allowed me to leverage the computational capabilities of Python while harnessing the thermodynamic calculation capabilities of backstage, as you all know. Let me summarize the high throughput screening methodology employed in this work. The diagram below illustrates the process. Each composition within the defined composition space undergoes a basic equilibrium calculation, and it is subsequently filtered based on predetermined criteria to ensure the desired alloy chemistry and physical properties. Remarkably, approximately 10% of the entire composition space successfully passed through this initial criteria. The remaining compositions are subjected to the more advanced and computationally demanding criteria. Combining the resulting data set with feedback from project partners, we identify and report the most promising compositions at the final stage. At this step, the screening results undergo fine-tuning, which is performed interactively with the user as well as our results database. To understand the behavior of compositions at high and low temperature, two sets of equilibrium calculations were performed at 500 degree and 1000 degrees Celsius. In this purpose, already 1.5 million equilibrium calculations were performed, and the thermodynamic data was later stored in a dedicated database. This data includes the amount of phases and phase constituents for each composition. A characteristic ID was assigned as a key variable for each composition to store the data reliably. The thermochemical data set is further screened by subsequent criteria. And this step is called the Roth filtering. So to provide austenitic solidification and martensite formation, we applied criteria based on phase formation. Therefore, we investigated the stability of FCC phase at 1000 degree and the BCC phase at 500 degrees Celsius. Additionally, we ensured that there is no graphite formation at both temperatures. Accordingly, only 8% of the compositions remain after the initial filtering that gives us 66,800 compositions that satisfied the thermodynamic criteria. Hard-facing alloys typically contain these carbides or borides as hard precipitates. You can see this further step of categorization now. That gives this hard precipitates gives the coating ability to resist abrasion and increase the bulk hardness of the material. And however, the mole fraction of the embrittling hard phases should be less than 10% due to their detrimental effect. Based on the benchmark patent, phases are categorized into 5 groups to control the fraction of these phases. Combination of 12 elements resulted in 300 possible phases for each composition. Remember that how many compositions we had in the beginning. You can see the example for a phase categorization of a single composition at the left-hand side. A phase matrix is generated to determine the category of each phase. In some specific cases, phases can belong to 2 categories based on their elemental compositions. For example, if you look at the FCC A1 phase, it is only considered as a matrix phase when it had a carbon fraction less than 0.1. Embrittling phases such as M7C3 are assigned to bad carbides and borides, whereas hardening phases such as M3B2 assigned to the good carbides and borides categories based on our reference patent. At the right-hand side, you can compare 2 compositions with different ratio for phase categories. If you look at the composition ID1, it has no bad carbides or borides. Therefore, could be a better composition, better candidate when we compare to the composition number 2. Now I will introduce 2 more advanced equilibrium calculations. These are expensive calculations. I mean, more time is required to handle these calculations when compared to the previous ones. Here, the melt range refers to the temperature range between the strengthening intermetallic phase and the phase-centered cubic matrix phase. It is expected to be maximum 250 Celsius to avoid the cracking. Firstly, I did precipitation target calculation in order to get the liquidus temperature. Below 250 Celsius of this equilibrium calculation, then I check the FCC matrix phase is stable. So for each composition, first of all, we need to determine what is the liquidus temperature for that particular composition. Then we need to do one more equilibrium calculation at 250 degree below and ensure that FCC matrix is still stable. And after this calculations, we again apply one filtering and we omit the phases that not suit this condition of melt range. And then we end up around 10,000 suitable compositions. Another crucial aspect for improved alloy design is the prediction of the Martensite start temperature as a function of composition and austenitizing conditions. We have calculated the Martensite start temperature based on a temperature model by Van Bohemian and considering the change of the free energy difference between FCC and BCC phases, also at a temperature increment. The model is developed on a basis of a systematic analysis of delta G data calculated with the FS Steel database of FactSage. Using this approach, the Martensite start temperature is estimated for each promising composition. Here is our user interface I created to interact with results based on provided information from our project partners. We bring a completely new quantity, it's the raw material price per kilogram, that can be inserted to estimate the cost of each composition. Bad carbides and intermetallics can be limited to the desired percentage. Here you can see I set them to 0%. And after that, I got 2,038 promising compositions remaining. Compositions are then presented in a graph by their approximate price and the calculated Martensite start temperature based on our model, as you can see in the next screenshot. So you can also see that this example where I limit the liquidus temperature so that the compositions with the high melting temperature are kicked out. We can also fine-tune the composition of interest by percentage of alloying elements if required. Density of each composition is calculated using our machine learning-based AMP database. What's specific about this database is while conventional databases do not cover a wide composition space, with AMP we have the possibility to easily screen almost the entire periodic table. After careful consideration of the results, compositions that stand out have been reported to our project partners. Here you can see the two compositions that satisfied the design criteria for the hard-facing coating material. You can see the BCC formation, FCC formation, the melt range, and all the empirical phases omitted at high temperature. These are all satisfied in these two compositions. Also, you can see the exact value of liquidus temperature, price, Martensite start temperature, and density. Before summing up, I would like to introduce our new tool, the CAM server. One of the standout features of CAM server is the ability to perform high throughput calculations using CAMUP. This means that the complex calculations can be carried out with remarkable speed and efficiency, allowing the user to process a lot of data, vast amounts of data. The CAM server will be hosted on a dedicated server, and this will provide the optimal performance. With CAM server, the most important thing may be the flexibility. So the user can input any number of variables such as temperature, pressure, and concentrations of various components. And this will enable to explore different scenarios and analyze their thermodynamic equilibrium conditions. The calculation results are then exported to a user-friendly SQL databases or more easy to handle CSV files. Then it ensures an easy access for post-processing to the user. It is designed to support the research and progress in material design as well as process modeling and optimization. Finally, it is good to mention that this is currently only an internal tool for GTT developers that we get experience from. However, it might be available to our customers at some point of time, so please reach us out if you're interested. To conclude, high throughput screening enables exploration of the chemical compound space, providing a valuable approach to address the growing complexity of material design and processing. And by harnessing the thermodynamic calculation capabilities of FactSage and the versatility of Python programming language, one can efficiently and reliably compute and analyze millions of equilibrium calculations. As we say, the more than 3.5 millions of equilibrium calculations were performed for the screening of hard-facing alloys that I presented today. Approximately 2,000 compositions out of 700,000 satisfied all design criteria, and 2 compositions were presented as the potential candidates. Finally, the CAM server is currently under development as our new high-throughput calculation tool. It follows a materials informatic approach. I would like to thank all of my colleagues who supported me during this work and prepared this workshop. Thank you very much for your attention, and I am glad to answer if you have any questions. Thank you.